Okay. If I take my population and I do a sample, I get a sample statistic. But here's where things start to go slightly askew. I want to measure, I don't know, the average score a student receives on the MBA exam. So they have to take the graduate, I don't remember what it's called, GMAT, graduate material aptitude test. I don't remember what the initials stand for. If I knew everything about the population, I could tell you the average. But I only asked the students in my MBA class, hey, how'd y'all do? Now, I'll give 5 numbers. Now, the people who run the exam, they have all the information. They know that there were 2,637 people that took the exam that semester. But I only have 5 of them. So I only get to ask 5. I don't know the following information. What I do know is my group. So I say, I'm going to take a sample. But maybe I have a friend who also teaches the MBA course and I ask him for a sample. There are several faculty here who all teach these MBA courses. I can ask all of them for a sample, but only give me 5. The result is that out of the 8 faculty, I get 8 different samples of 5. Notice each of these has 5 data points, and there's a little red triangle on each line. This is on page 274. That little red triangle is the average for that group. Notice that even though some of these individual groups are very widely spread, if I only look at the averages, they all get a lot closer. What I've got here is an example of sample variation, sampling bias in some fashion. Now, this is actually not a fixable bias. It's built in. Every time I take a random sample, I may get people to one side or the other, and I get real outliers. If I actually had all the data for all 2,637 of them, I would see this distribution, which is on the previous page, but I don't know this. I don't get to see this. This is what the people who wrote the exam, they see. I only see the group I asked, right? This is the problem. There's some mean, there's some standard deviation, but I have my mean, and I have my standard deviation. So I've created a point estimate. And I can think about the error. If I knew the population mean, I could say, well, how far off was I with my sample? And we can call that like the sampling error. my random sample is what gave me X bar. It's what gave me S. That means it's a random variable. And if it's a random variable, it should have a PDF. And that means I can use what I know in this PDF, estimate my population information that I don't know from my sample that I do know. But there are going to be some things that both help and hurt me when it comes to figuring out what sort of variation I've got, what sort of estimating ability I've got in terms of all of this information. And there are four primary factors. The first of which is sample variation. Like I said earlier, I might have a class that did particularly well on this exam because I'm a great teacher. I might be a crap teacher and these people did really horrible. I don't know, but I can look at my estimate, right? So there's some variation in the sample. If it was truly a random sample, not just a convenience sample, I might even pull the same person twice if I'm sampling with replacement. Same thing about the population. I can't control either of those things. There's no way for me to know in advance how varied the population is or how varied my sample is going to be. What I can control is the sample size. And how close I want to get. Now, this is a weird one to think about. But I'm trying to figure out the population average, and all I have is a sample. And maybe I can say, well, I want to be 95% sure, 90% sure that I've got the right answer. Or I want to be within a certain tolerance. This is where I switch what I'm doing. I switch the way I'm thinking. In all the previous work we were doing, we had all this information. We knew it. I have all the data. And then I build things about the experiment from the probability, from the theoretical stuff I knew about this setup. This now changes. I don't know what happened. I just have the pile of data. So I've created this estimator. The estimator is my statistic, and it's used to approximate, to estimate, the parameter from the population. So I can think of my sample average as approximating mu. I can think of my calculated proportion as estimating the proportion in a population. I can think of my standard deviation as estimating the standard deviation from my population. Now we've got formulas for X bar and S and P here, rho. And the idea is to infer, to take from these specific examples and infer something about the population. Jacob.
So are we calling these equal?
No, they're not equal. That's an important point. I don't know that my sample average is exactly the population average, but I want to know how close. Or at least I want to be able to estimate, well, if I came up with 80, then I can say, well, the average must actually be between 77 and 83. I don't know where it is, but here's my interval. And how confident am I that that's the right section? And the way I determine that confidence is going to be based off more information I know. More questions?
These using the exam of
No, this is the next chapter after the exam. But since I've got lag time on stuff being handed in, I figured I need to keep going. What I would really like to have is a good estimator. I'm using these, but I would like to know what makes an estimator a good estimator or a bad estimator. Hmm. There are a couple of characteristics that all estimators have, and my goal is to either maximize or minimize those characteristics to make my estimator better. One of those characteristics is bias. If I have an estimator, T, for some parameter, theta, then the bias is the expected value of my estimator minus the actual parameter. I would like an unbiased estimator. I'd like that value to be 0, or as close to it as I can reasonably make it. A good estimator is unbiased. Now, since I don't actually get to know the population parameter in advance, I might not know whether my estimate is biased or not. But what I want to think about this is if I do this experiment a bunch, if I take my sample over and over and over, and I figure out what's going on, how many times did I underestimate? How many times did I overestimate? And if on average my bias is 0, then I'm doing okay. So for example, both the average and the proportion are unbiased estimators of their respective parameters. But it turns out that standard deviation is biased. It consistently underestimates the standard deviation of the population. This was our formula. Oh, there's a sum here. This was our formula for the population standard deviation. You take the difference between the average and the item, you square it, you divide by how many things are there, and we add up all of them. This is underestimating sigma. Oh, sorry, this was S. Underestimates sigma. And that's why, if you remember, what's our formula for S? What's the difference between the population one and the sample one? STDEVP versus STDEV.S.
Is S like the more smaller one, the sample?
Yes, the S is the sample one. But why? What do we do to fix that underestimate?
We try to estimate like a little bit more, try like to.
Right, but we did something specific. Jacob?
-1.
There was an n-1 in the bottom. And when you divide by something that's a little bit bigger, doesn't that change the value? So we change our overestimate. This in the bottom. This is my Bessel correction. So I can take a biased estimator and kind of adjust it to make it less biased. So I know that it is possible to think of bias differently, to change that. Sampling error is random. Bias is systematic. Here. I'm pretty sure I talked about this example before in this class. There is a military distance shooting competition. Did I mention that in this class? Okay. I want to use that target image a little bit better. Page 276, I've got 2 pictures of a target. These 2 shooters have the same spread to their shots. The variation is the same. But these guys are shooting right, and these aren't. So here is a bias. They're pulling to the right. Now, if you're shooting a rifle, you can adjust the sight to fix that. That's our change, right? You adjust the horizontal displacement of your optics. But if you're shooting without a sight, you have to adjust your grip, your stance, and your hold on your weapon. I don't shoot. It's been years since I held a rifle. Good God. It's been almost 40 years since I held a rifle. So it's been a long time for me. But this idea of I'm really centered on my target versus I've drifted consistently in one direction. That's my idea of bias. There's a particular lean to the outcome. So I'd like an unbiased estimator as often as possible. So the goal is to minimize bias wherever possible. By the way, this is not restricted to physicality. Bias can occur in the way a question is phrased, in the way a survey is conducted, in the interviewer themselves. If I were to ask about, in a survey, a face-to-face questionnaire, I'm going to walk around campus, I'm going to ask people questions. If I walk around asking questions dressed like this about drug use, anybody going to talk to me? They're going to think I'm a narc. I'm from the DEA, I'd like to ask you about drug use. No, they're going to run. So bias doesn't have to be endemic to the object. It can be imposed. Dr. Dropa, in doing some surveys of local businesses in Greensburg, wanted specifically to conduct minority and women-owned business surveys. They wouldn't talk to white male students as openly as they would to non-white and non-male students. Bias is in perception. I can think about an estimator's efficiency kind of in reverse or inversely to its variance. If I think about my samples and I think about the distribution of my sample, if my samples are all over the place, my estimate is probably not as good as if my samples are tightly clustered. Another set of targets for you. An interesting idea. The average of both sets of shots is identical. If you find the point that all of these shots are centered around, it's the same in both pictures. But this person is a wilder shot than this person, right? They're on target less, even though on average, their targeting is exactly the same. So if I can have a higher efficiency, I'm getting closer to the right average faster. It needs less variability in my distribution itself. So the smaller the variance is, the more efficient my estimator is. So I want to increase efficiency or minimize variance. So again, I think of wanting to increase or decrease something. In this case, I can think of it either way. I either want to think of increasing my efficiency or decreasing the variability in my sampling process itself. Guess what? I really like to do both. And we do this frequently. A minimum variance unbiased estimator. When I can find these, I'm going to be really happy. In a normal distribution, average, not standard deviation, variance, and proportion are minimum variance estimators. S squared, S squared, and P are M views for mean, variance, and proportion. This is one of the reasons I really like normally distributed data. Because when I have a normal distribution, I've got minimum variance unbiased estimators here. I've got good estimates. With a uniform distribution, I don't have as good as an estimate because my problem shows up in the spread because that's not well concentrated. It's not small variance. It's big variance. There's one other idea. I'd really like an estimator that is consistent. And consistency for an estimator is related to not getting further away as my sample gets bigger. If I did instead of taking 5 students in my group of MBA students, maybe I took 10 or 20. What I'd like is the variation and the variability to go down and the average not to suddenly wildly change because I took more students. If I think about the targets, I'd like to say as I shot more and more, I don't suddenly see more wildly occurring, or all of a sudden everything walks 5 or 6 inches to one side. I didn't suddenly have a change. If I'm thinking about a normal distribution, what I want to have happen is something like this. With a small number of samples, I can get a large variation. I only took 5 students. Maybe I had somebody do really badly and somebody do really good and 3 other people. So I'm going to get a really wide standard deviation. But if I take more students, I expect the clustering around the average to get closer. And if I take even more students, say 80, I expect that clustering to get even closer. I want my variation to go down as my sample size goes up. Best part. For these three, that's also true. For all three of my previously defined estimators, average, variance, and proportions, they are also consistent. So they're not just minimum variance, unbiased, they're also consistent estimators. Larger and larger samples give me better estimates. And if I go back to my list of things that were uncontrollable versus controllable, this is controllable because I can take larger samples as long as I can afford to do that. Here is, in my opinion, one of the deepest results in probability and statistics ever. This average is a minimum variance unbiased estimator for the population average. Let's think about the sampling error. So I'm going to think about the standard deviation. But this is not the standard deviation for the population. Remember, the population is this big amorphous thing I don't know about. I took a sample. I want to think about what I know about the variability of my sample. The bigger my sample is, the smaller I want this to be. So I'm going to define a new idea. The standard deviation for my average. Notice I put that little X bar down there. As opposed to just writing sigma. Well, this turns out to be related to the one for the population. And here's where my consistency comes in. What happens as n gets bigger and bigger and bigger? What happens to this number as my sample size increases?
Gets smaller.
Because there's an n on the bottom, right? And if that denominator gets bigger, the whole fraction gets smaller. I'm going to call this the standard error. Of the mean, since we're doing averages. Now here's the interesting statement. If my population is normally distributed with some average and some standard deviation, then my sample average is also normally distributed. Ready for the best part? that normal distribution will have the same average. And its standard deviation will be the standard error. Wait a second. What? I take a population that's normally distributed, heights. Heights are normally distributed. I take a sample of 10 people. I do that sample over and over and over, and I get a new PDF. The new PDF is a normal distribution every single time. Bottom of page 277. If my population looks like this, that's a normal distribution. Then my sample distribution looks like this. And as my sample size goes up, this gets narrower and narrower and narrower, which means I'm getting a truer and truer picture of the average. The fact that I'm getting a normal distribution from a normal distribution is nuts. But the real big question is that part. What if I didn't have a normal distribution? Electronic equipments. Things like hard drives, light bulbs, or flashlights, battery connections, power cables. All of these things have a different kind of distribution. If you think about light bulbs tend to either burn out really quickly or last a very long time. So if I look at the distribution of how light bulbs behave, how long is a light bulb going to last, it's not a normal distribution. The distribution for a light bulb actually looks something like this. That's definitely not a normal distribution. You can't have negative times a light bulb's going to last. So this only starts at 0 and goes off to the right. It's not symmetric. Yet, if I start taking samples of light bulbs and I look at the distribution for my sample average, I still get a normally distributed image. The central limit theorem says no matter what your population distribution looks like, sampling distributions always look normal. Let's suppose I have any population. I don't care what the graph looks like. It could be uniform. It could be my funky light bulb one. It could be normal. It could be something else. It could be skewed terribly. It could be rigged beyond all methods of device. But if I know the average and I know the standard deviation, then the PDF for sampling is normal. It gets closer and closer to a true normal distribution as you repeat the sampling. Now, my first reaction on seeing this was bullshit. The first time I saw this theorem, I went, that's not going to be true. Let's take a uniform distribution, dice. I'm going to take a standard six-sided die. That's uniform. And I'm going to roll the die 10 times. I have no idea what to expect. But we know the average for that distribution is 3.5. And the standard deviation is the square root of 6 minus 1 over 12, which is some weird looking number. So I roll my die 10 times and I get an average, but I'm going to get a pretty big variation, right? Then I roll my die 100 times. Well, the variability on the average of those rolls is going to go down. If I do a sample of 10 individual rolls, that's one sample done 10 times. Here's a sample of 2 rolls done 10 times. Here's a sample of 4 rolls done 10 times. Here's a sample of 8 rolls done 10 times. The averages are getting closer and closer to a normal distribution that looks like it's got its center at 3.5. And its standard deviation is getting smaller. This is a completely different distribution. I'm getting closer to that normal distribution. Now, I must tell you that I thought this was crazy. I did not understand why this worked. It took me quite a long time to get the why of this working. But if you want to see it in action, Grant Sanderson, who runs the YouTube channel 3 Blue 1 Brown, did this experiment. He took a computer program and told it to roll a die over and over and over and over and over again and charted his sample of 10 over and over and over and over again. And then he took the die and changed the faces. So instead of having the numbers 1 through 6, he had 2 1s and 4 6s. That's clearly a very different distribution, right? He did it again. Guess what? Sorry, 3 1s and 3 6s. Same average. Different standard deviation. After 100,000 rolls, exactly the same normal distribution. And you can watch it happen. The video is linked in the web link section of our campus page. It is about 15 minutes total. The demonstration portion of the central limiter is about 5 minutes. It is astonishing to watch. In general, the problem is this as n increases line. I really need to know how big a sample size I need to get. The picture showed me sample sizes of 8. I really want to look at larger samples to try and get closer. The central limit theorem really only becomes useful with a sample size of 30 or more. A general rule of thumb. I'm going to abbreviate central limit theorem CLT frequently, so you're going to see that. Usually, if my sample size is bigger than or equal to 30, that's enough. In general, any distribution will give rise to a normally distributed sampling ID, provided I have a large enough sample. If I don't know whether or not I truly have a large enough sample, I can fudge this. But now I get to ask the question, Jacob, how big is my interval, right? I came up with this estimate. How good is it? But if I know that my sampling distribution is normal, then I can ask, how good do you need it to be? Tell me how confident you want to be. Do you want to be 90% confident, 95% confident, 99% confident? How confident do you want to be that the interval you are telling me is going to contain your population average? Why do I care about what percentage you want to give me? Because it's normally distributed. I can then figure out how far out I have to go to get that much area in the curve. I need z-scores to do this. And my choice of z depends on what I want for a confidence level. I did the clock. I will see you all on Monday. So.